let me start with the discussion. Monica talked about the customer. There were definitely 3 issues. One was related to what are the licensing terms. So I think there is a talk and discussion later, which I'm not that involved in the licensing, but there are other experts. Second one was the monitoring and observability. That have not been great in 7 or 8, and there have been significant improvement. And I've seen there are other talks talking about the monitoring part. So this track also does not cover the monitoring. My expertise comes more from the benchmarking area and be able to performance and responsiveness. And that is where, when I got this email from, that was just 1.5 months ago or so, that hey, we are evaluating this Intel latest platform, and I'm doing this runs and I'm getting a variability of almost 40, 50, 60% from run to run. And I'm like, no, I have not seen such things. So you can see the 2 metric he was talking about. One is full capacity metric, when system is fully utilized. He said that is just only when, in case of everything else fail and only few system carrying the load, then performance is very repeatable. But where my production range is with regard to 30 to 40% operational, then I see this 60 to 70% variability from run to run. And that start gave me some idea, okay, what is going on here, because we don't see such things. That lead to me asking the very first question to the person, that what are you running? And when you look at, this is a pretty large company. They said, I have around 3,000 to 4,000 applications. Some of them are very small footprint. These are microservices which talk to each other, and some of them are very small, like 2 gig. We run them visually 2 gig or 3 gig heap. Very few of them are very large. We go up to 100 gig heap. And the problem is, he said, I cannot take anything from my production environment and have the confidence of repeatability running on the systems. So then what I go run for traditional benchmark, etc. we find. And one of the benchmark he was using, we'll talk about later, that he was using a benchmark which he said, we have matched it to we run our system in production, so we know the behavior, and we have done the benchmark part, and they pretty match with regard to whether it is GC or it is CPU utilization or network IO in most of the situations. So we have created this proxy where that's what we are running. So okay, so that's even help us because we can run similar proxy. And when we landed up running on our environment, so let me see some of the component I could figure it out. So the traditional environment could be your app and JVM. It could be running in a container, and from that container, when you launch a process, you could have number 1 case. You launch the process, it goes to one of the socket. This is a 2-socket system. The process will start on, let's say, the other end of the socket, and it will get the local memory. So number 1, you're running on a socket is getting the local memory. In number 2, you start your process, it starts on other socket, and then it does not get its own local memory. It gets the memory from the other socket. These are the traditional 2-socket system. In third case, what happens that you launch the process again, and you in the second socket, and it gets local memory. So now let me ask the question that, are you going to see the best performance between 1 and 2, which is going to be better performance? 1, because the local memory. And that part could cause significant variation in certain cases. It will not result in, based on application, on the total throughput, because we are talking memory latency of 100 nanosecond to 140 nanosecond. But it can make a big difference on your response time, the latency. So anytime you are sensitive to latency, that path can make a big difference. So that is one variation for the responsiveness, of why the responsiveness could be different, but not the total throughput. Second part, which is not covered just on that picture, are many of you are maybe using the containers or the virtual machines. And when you're setting the thread pool within your application, it depends on how many CPU thread that API call gets it. And that answer to it, if you're running on a large system, would be all the core. For example, this system was 112 threads. It could be 112 thread. Or if you're running within a VM, and that VM only gives you 16 thread or so, answer would be 16. So in one case, you would be setting your thread pool based on 112, another just on 8 or 16. And as an app writer, you don't have the control. It's in the deployment scenario you have to see. And we have seen on the thread pool, if you, based on fork joint or now the parallel stream, I will talk a little bit later, that how do you do the settings, it could have an effect on the context switch, etc., and resulting in variability. The another part is also your guest OS policies, like some of them, Docker, etc., they allow pinning, other VMs don't allow pinning. And your performance, thread moving from one socket to other, could have significant impact. And the last part is on the heap memory. That was the surprising one from the experiment working with that person. What is happening that there was around 256 gig of memory on that system, but traditionally a system will be keep using for almost 2 days, 3 days, 4 days, not rebooted. So over time, the memory fragmentation happens. So even though you are requesting a 20 gig of heap, you may not get 20 gig of heap. What we notice on it, sometime you were getting 18 gig, another time you were getting only 8 gig. And I'll show some data later. So even though you give the parameter of like, give me this much heap based on how much fragmentation have been, and if particularly the transparent large pages, which by default nowadays are enabled, that requires a chunk contiguous. If it is not the large pages, then it could actually give you much more easily those memory. And then, but there is a performance benefit of large page of 10 to 15%, and that can make a difference on the responsiveness also, as well as throughput. So earlier it used to be you have to request the large pages. Now the large pages in these cases are all by default in the transparent. You don't know. So these were the interesting things. So some of the things, I did not mean the talk today to go about these detail, how the process launch, etc. The interest was, can the JDK 8 to 11, are any of the benefits which are changing, does it help in reducing the variability? Because these parts are out of your control. As a programmer, as a developer, you are not thinking where it is deploying, what are the policies, because their policy could change. The deployment might be MISOS here, tomorrow Docker, or some other things. So what we wanted to see is the JDK doing anything, and could be done certain changes which help. So that is where one of the thought was coming. So the couple of things we wanted to talk about with regard to some idea. First, we wanted to give you something about what are the big changes from 8 to 11. And this talk is not about those changes. I think you are very well aware, and there are other talks which talks about those feature of the API changes or some thread pool changes and some data coming on them. What we wanted to show that if you really run certain benchmarks and workload, how the different parameters by default are changing. That's one of the sharing part. Another part we wanted to show you the data for, again, we talked about throughput, we talked about the responsiveness, we talked about the variability, and some startup. So that data we want to share. And when we look at, there are a lot of variation in those parts. So Monica looked at some of the explanations that why it is going that way. So it will help you to understand. So let's start with the new use cases, if you look. So there have been changes with regard to monitoring, code observability. We are not covering it on that part. There are new uses of the containers, microservices, or function as service, or polyglot programming. We will cover the function as services slightly, that what you could see the impact from the JDK 11. And then for the concurrency part, we are not covering the project Loom, and the value type are not there, but we would definitely, one of the benchmark has the fork joint, and what is that impact on the thread pool will have. And the networking part is the benchmark using NIO, using Grizzly, but not the Netty, but the impact is very similar, but we are not going in detail of that part. So most of the data you would see from the benchmark, which are throughput or responsiveness or variability or the startup type, the data. So So let's start with why did we pick the JDK 8, not 7, not 6 or so. And one of the reason was, this is from one of the survey, that almost significant amount of deployments currently are at 8. That's what they are evaluating, and they are thinking to move to 11. That's what. Another part is which workload did we avoid, because we did pick certain workloads, and what we are finding, the JMH particularly, which comes with the JDK kit, has a lot of variability, almost 50%, and some of them even bigger. So we are not using the JMH component, even though they come with OpenJDK, and many times you might just look at the data coming from OpenJDK. So that has a lot of variability, and we had to remove that part out. The next one I talked about a bit, heap, that in that process, even if you give it a certain amount of heap, you are not guaranteed. So you should always put your GC print output into checking environment when deploying how much heap are you really getting. And the data shown here is really for a spec JVM 2008, which is compute and memory bound different components. And what we wanted to show, just look at the 20 gig to 60 gig part. Some of them, of course, there won't be a difference if they are not allocating heavily and not getting impacted by that. But there are many components in your environment also which can have a significant impact, just how much heap did you get from run to run. So that data was just to showcase that even on your cases, when you have wide variety of them, you would have big difference. Now let's look at the throughput and performance. So spec JVM 2008, it has almost 13 or 14 components, and we look at least for JDK 8 to 11 and even up to 13, there's almost no case where the performance goes down, and it's improvement only. So by default, if you just move from 8 to 11 to 12 or 13, then other than very rare cases, you should see an improvement just by default. That's just the parameter I put for the slides. Now let's talk about a little bit more performance, responsiveness, and variability, because you can find many benchmarks which is a throughput. You run them, there are so many of them. For performance and variability, the one of the benchmark which at spec, Monica was also part, Monica and I work in the same committee, we created this benchmark for this purpose, that you can have all three components. So the very first one here, when the benchmark runs, is spec JV 2015. In the beginning phase, it actually doing a binary search. That means it is loading the system crazily, some low value, high value, low value, high value. So very similar to production environment, where you might see the surges in throughput or the load coming in. And at that time, it determines what is your settled load values. So it tried to give you a rough approximation what kind of load you handle when the request comes in very variable or bursts. The second part is we call response throughput curve, where it slowly increases the throughput and it keep increasing, and it keep measuring your response time, and it is a 99 percentile response time. And from that, it keep loading the system, and you get two metrics. One is the max jobs, which is the full system capacity. What will happen if your system is the failover mode and need to handle. And the second one is the critical jobs, which has a SLA that which is a geometric mean of 5 SLAs, 10 millisecond, 25 millisecond, 50 millisecond, 75 millisecond, and 100 millisecond. So it try to check what is your throughput when you have those SLAs, and that is called critical jobs. That is more responsiveness, and we have seen for different scenarios, it is in the range of 30% to 50% of the system utilization, and that is where most of the production environment system also operate. So these are the three metrics from this benchmark we get. So now let's look at some of the data we got. So this data is for the JDK 8 to 11, and it is full system capacity and responsiveness. What you will see between 8 and 11, that full system capacity almost no difference, and you may be surprised in one of them why. And what we have seen, I talked to the person in the team who works, several of the JIT related changes, even for 11 and 12, they have been backported to JDK 8. So if you pick the latest JDK 8, several of the JIT related changes are backported. So throughput wise, you would see the very similar performance for many situations. That's the reason. The responsiveness, the critical jobs part we were talking, that got impacted by your response time for each transaction, because that is what for SLA is measuring, and that is where we see almost a 35% improvement from JDK 11. And the reason being, it is that 11, when we look into detail, it's mostly the G1 GC, because your JDK 8 by default has the parallel stop the world GC, and anytime you are doing a GC, it ended up stopping to anywhere from 50 millisecond to almost 300-400 millisecond based on what kind of GC happened. On the other hand, G1 GC takes a hit on the full system capacity. That is why both are matching kind of, but it gives you much better critical jobs, where the response time is never more than 20-30 millisecond, and Monica will cover later more detail why and how that happens. But that is the part of the reason the responsiveness is much better on JDK 11, not due to any other component, but on the G1 GC by default. Let's look at the variability part. How we are defining variability? It is more that we are doing 10 runs or more, and then we look at how the total maximum throughput or the critical jobs we were measuring under SLA changing. That is run to run variation. That is very similar to you take your test case and launch it 10, 20 or 30 times on the same system. That's what we did also here, that we do some other work in between and then launch this system, do other work and launch this system. And what we are finding that from the variability perspective, JDK 8 on the throughput, standard deviation is around 2%, but standard deviation for the critical jobs, which is the responsiveness, is almost 10%, very high and really bad. On the other hand, JDK 11, which we talked about due to G1 GC, much more I say the response time which is predictable. On the other hand, the parallel GC stoppages are not predictable. They can be from very small to very large, and that's what causes the variability part. Again, the variability is also related to G1 GC improvements. So that is the main component we are finding, in addition to, of course, the API other thing you get by default. It's mostly variability and responsiveness coming from the G1 GC part. Now let's talk about a bit more startup type thing I was talking about, because when we are going function as service, then we are all talking about something coming out for almost few milliseconds to say 1 or 2 minutes. So far, any workload we were talking at least 10 minutes, 6 to 8 minutes to almost 2 hours running. Like Spec JVM 2015 runs 2 hours. Spec JVM 2008, each iteration runs for 6 minutes. Overall runs for 2 to 3 hours. But the Capo benchmark we just picked, they have improved the repeatability. I really don't like a bit their repeatability, so we are doing several runs. But what it is that you can see on the top graph, several components are barely 500 millisecond each iteration. So small, which would be very similar if tomorrow you start writing function as service, a service need to make a call, get the work done and be out. Then what we are finding that in that case between 8 and 11, I was surprised that so far we were seeing JDK 11 is better in everything compared to 8. Better, similar throughput or better, and much better variability and much better responsiveness. But here I was surprised to see that in several of the components JDK 11 is actually, first I looked, oh, the higher is not better, it's lower because I'm dividing JDK 11 execution time by the JDK 8 execution time, so lower is better. And this one again I discussed with Monica, and then she looked into the logs. It happens to be this time G1 GC is not doing good, and she would have explanation why in particular for these kind of instances. So there are situations where G1 GC for this short startup or function as service type scenario, and we plan to investigate more and give feedback to OpenJDK. That's the part we plan to do. So I think that's the part I wanted to share the data and I work with Monica and she had the explanation for several of these things we worked on.
Cool. Thank you, Anil. So, so all the good fun stuff that was covered by Anil. So what I'm going to do here is provide a little bit of groundwork on garbage collections, and certain observations that Anil had. I'm going to provide explanations for those as well. So very basic stuff with respect to a heap layout. So usually we talk about heap as a contiguous chunk like that. With the newer garbage collectors, you would also see something called regions. So that's a regionalized heap, basically, where they have, so these are all virtual space, right? And then there's also the concept of generations. So you have the young generation and old generation. So in, for example, G1GC's case, you will have the generations as well as the regions. And so that's typical configuration of the heap when we are trying to explain the basic heap layout. So for now, ZGC and Shenandoah are not generational, and G1GC is generational, as well as it's got regionalized heap. So I have also in some of the, because we're comparing JDK 8 and JDK 11 or 13, I've also provided numbers for parallel GC. And parallel GC used to be the default for JDK 8. And starting 9, the new default GC is G1. So that's why I wanted to provide comparative numbers. So parallel GC is not regionalized. I will go into details of this later when we talk about da capo, but something to realize is that when we talk about generational heap, Eden and survivor regions will form the young generation, and old regions as well as humongous will be from the old generation. So this is very important to know, and I'll go into details why. Okay. So the same for a user or even a GC person, it all boils down to occupied and free regions. So basically, if you're generational, basically your young generation gets filled, and then you either promote or you try to age them in the survivors, and eventually you will have just a bunch of occupied, so basically long-lived objects or whatever. So again, it's just all the free regions are maintained in a list, and any of those occupied regions could be, like I mentioned, young or old or humongous, which is allocated out of the old region. I want to quickly compare different garbage collectors, and the reason I wanted to talk about the other two, like Shenandoah and ZGC, is because that's the future. That's where we are headed. So you'll see this trend, which I'll cover here soon. And so basically, the entire thing boils down to copying. Okay, so I'm going to emphasize that here. So we also know that as compacting collector, or we call it evacuation as well. So it's kind of similar. Everything is similar. Your heap has a from space and a to space. And as you start filling up the from space, and it gets filled, now is the time for you to do marking. Okay, and to do marking, you go find out the GC roots, which could be a static variables, that stack, any references, GNI references, and then you identify them in your from space area. And then you start doing the live object graph, and eventually you move the live objects to the to space, and then you reclaim the from space, and eventually the to space turns into from space, and you start allocating into the from space. So it just goes back and forth, right? So this simple concept, the way it gets a little more complicated when you have generational GC. It gets complicated when you are doing concurrent compaction or concurrent marking and stuff like that. I will not have time to go into details, but I wanted to, sorry about the formatting, but I wanted to quickly highlight the differences. So as I mentioned, parallel GC is not regionalized, right? But it is generational, just like G1 GC. Compaction does happen in parallel and G1, and they just used the forwarding address in the header. And because parallel GC is throughput driven, so that's the goal, is to have higher throughput. And there's no pause time target per se, as long as we keep on putting the throughput to the max. So everything is stop the world in parallel GC. G1 GC does have a target pause time goal, and so I'm not going to go into details, but basically it's like I hope I can achieve this goal, and then the adaptive resizing of regions or a collection set in the regions will be what will be changed, as well as you will find out how much expensive a particular region gets during a collection. Parallel GC does not have any concurrent marking at all. It does everything is stop the world, like I mentioned, but G1 GC does, and they are both G1 and Shenandoah are snapshot at the beginning algorithm, and ZGC does striping, which I'm not going to go into details here. There's also the concept of colored pointers in ZGC, and their target pause times are slightly smaller, actually, than G1 GC, because both Shenandoah and ZGC are targeting the low pause time market, right? And so I quickly ran JBB with about 28 gigs, and what so this was explained by Anil earlier. Max throughput is basically the entire system. When you just fully load it, that's the system capacity. There's the response and throughput curve that Anil was talking about. That's the one that I'm talking about. That's the max JOPS metric. And then the responsiveness is what he mentioned as critical JOPS metric. Everything is normalized to Shenandoah's max throughput. So the things I want you to take away from here are that parallel GC is everything is stop the world. So of course it gives you the maximum throughput. That's the way GC is designed. Generational, stop the world, so it gives you the maximum throughput. But as you go down to G1 GC, and basically what I've done is like made some adjustments to the pause time goals, kind of relaxed it a bit. So that's why you see that your throughput kind of gets better, but your critical JOPS is pretty consistent. So the last three are basically your G1 GC. So you see how so that's where the repeatability metric that you were talking about, Anil, comes into play. As you change certain things with respect to, so the third and the fourth are parallel GC, a slight change in nursery produces a lot of variation in parallel GC's output with respect to throughput or responsiveness as well. Shenandoah and ZGC kind of have an issue here because they are not generational yet, right? And they achieve copying compaction via concurrently moving objects from the from space to the to space, right? So those are basically trying to achieve higher critical response time, which is what you see with ZGC. So it's kind of, it's 56, right? And whereas anything and everything that G1 GC could achieve was about 49 to 50, right? So that's the target, that's the goal, that's a design of these GCs. They're headed towards providing you much better responsiveness, okay? It's kind of like a lot of information there, but the trend that I'm trying to show here is that there's more effort put into getting better responsiveness, going from JDK 8 to 11 to 13. Okay. Now, going back to the Da Capo case, I wanted to quickly talk about G1GC and humongous objects. So G1GC has, of course, it's regionalized, so it has the concept of region. Each region kind of gets allocated a size at JVM start. In Da Capo's case, it was 4 megs. Okay, so if, as and when you have objects getting allocated, they would end up in Eden if they meet certain criteria. And if it's a humongous object, they will go and get allocated out of the old generation. Okay, so the threshold is basically the size of the object. So if the object is greater than or equal to 50% of the region size, so in Da Capo's case, if the object is 2 megs or larger, then it will be considered a humongous object. So less than 50%, it will be allocated out of Eden. Greater than or equal to 50%, then it would be out of the old generation. And anything that's greater than a region size would have humongous regions. So basically, that would be a contiguous space right there. So again, same information, but not, but like expressed differently here. Anything less than half the region size is not humongous. Everything else is humongous. If you need more than one region, then it's called a contiguous region, and it's also humongous. So with Da Capo, one of the things it does is does these system GCs to between every, I guess it's different benchmarks that start, and then but it's setting up the objects. So the objects are long-lived. And because of the 4 meg space, anything that's 2 megs or above becomes a humongous object. So when Da Capo is allocating these objects, which is hoping were regular sized, because of the lower heap region size that we have, these are all humongous objects. And when you're doing system GC, what's happening is you're trying to move these humongous regions. Remember that we're trying to have contiguous regions. You're trying to move it from the from space, because they're live, and into the to space, and trying to find, if you keep on doing it over time, trying to find contiguous regions it gets difficult because of fragmentation issues. So that's why the G1GC showed you reduced performance. Okay. I wanted to talk about AOT because that's something that's a direction again where we are headed is more responsiveness, and so there's we're going to have a talk later today about more JIT compilation directions in future by Mark. But this is something that is available since JDK 9, 10, and it's gotten better over time. And one of my colleagues has a very good article, so I'm going to reference the article here. Okay. So prior to tiered compilations, around before JDK 7-ish, you would have the first execution. It would end up in the interpreter, and then eventually you will have adaptive JITting. And based on the profiles of critical hotspots. So basically, it's like you have thresholds are crossed, some things get jitted, and there was a concept of server and client compiler, which is also known as C2 and C1, and then tiered compilation happened. So tiered compilation was fully supported in JDK 8, I think, and before that, it was experimental. With tiered compilation, again, the C1, C2 concepts are still there, but there's the profiling concept is different. So you have limited profiling as opposed to full profiling. There's a good explanation, like I said, mentioned in that link over there. So all you have to think about is basically from interpreter to C1 or C2 based on the profiling and the different thresholds. And then, of course, there's a de-optimization path as well. With AOT, what happens is we do not go, after the first execution, we do not go to interpreter. We actually go to AOT code. And we can do C1 and C2 based on full profile. So when you have C1 with full profile, you could go to C2. And any de-optimization goes back to interpreter. To go into details, please go ahead and read the article. And actually, there are many great articles out there on AOT as well. So what I ended up doing is using, interesting. So sorry about the the labels getting cut off. So what I did is I took the JVM 2008 startup component, and I tried to run it without AOT, then with AOT, and with AOT with tiered. The difference between AOT and AOT with tiered is that when you create the dynamic library, you could say that I would like it to be able to use the tiered compilation path, or you could say, nope, I don't need the tiered compilation path. So as you can see, higher is better. So most of the time you'll see AOT just giving you a straight up win for most of the startup workloads that I have covered here. And I apologize again for the label getting cut out like that. But what was interesting is if you look at the last three here to your right, so the blue one is without AOT, and after that the performance drops. So that was my so I was using the same workload as the one previous there, right? You saw AOT and AOT with tiered actually giving you a benefit. So these two workloads are the same, but the runtime is different. So that is just measured at startup, and this one is measured after it's warmed up, and now it's trying to achieve steady state. And the reason that actually the AOT with tiered gives you the worst performance is that it hasn't crossed the threshold. So when you think about these different compilation improvements, the thresholds change as well. So for example, tier 3 invocation threshold for AOT with tiered is more than 10x or 100x different than without tiered and stuff like that. So the thresholds totally change. So for this one, for the last one here, to achieve similar runs, I'll have to run it more times. So basically, if I would have run it more times, it would have crossed the threshold, and you would have seen a better optimized code. So it would have gone to tier 4. So it's like that's one of the reasons why we have that reduced performance there. I think I would like Anil to come back on stage because most of his work is amazing, and I'd like you to summarize, please.
Okay, thank you. So I think the main summary we want to take away from the JDK 8 to 11 or even up to 13 was, if you are running long steady state, mostly throughput bound, you may not see much difference between 8, 11, 12, 13, 4. There could be some cases where you are better, but usually we did not find across this benchmark a big difference. But if you're talking about workload with responsiveness, where you have the SLAs, you are looking at those low pause time, etc., you would see significant improvement in your responsiveness. And you would also see significant improvement in your variability. And the thing we found to relate to, it's mostly the changes from the parallel GC to G1 GC, because those pause time, etc., giving you more consistency and better response time, the end-to-end response time. That's what so if that is your goal on different application, then it is worth moving or evaluating up to 11 or even higher for latest GCs coming in. The last one is when you have the short running workloads, as we saw with the Kappa or so, you may want to check there, because there could be some issue with G1 GC, and we do plan to give this feedback to OpenJDK to see if they can be addressed, as Monica just pointing with the humongous object size is causing the issue, and you are seeing worst performance in that case. And we know that current trend, the last one was containers are being used very heavily, almost 40-50%, and the next one on the growth is the function as service in many areas. So I think that scenario will happen, so it would be good, I think, to have that part. But definitely right now you need to watch for G1 GC with regard to short startup timings related workload and situations. And as for AOT, Monica was just talking about, you have to be there also, just watch. If it is long term, then you might be better off without, but if it is short function as service type thing, then AOT definitely giving you faster response times. So I think with that, we definitely want to know more, because we are also in the spec committee working on making changes. As you saw, like earlier, the workloads were all like spec GBM 2008, more just throughput. You do something, compute, memory, and throughput. Then we change into spec GBM 2015, we change it into more response time, where you can see the difference on response time and repeatability. So similar changes we planning next, and we are looking into parallel streams and the other changes coming in. But if you have the use case from your area, hey, these are my problem point and these are the use cases, we definitely want to reflect them into the benchmarks. That is one of our goal. So they can be used to evaluation. As you saw that even to at least 3 or 4 large customer I have talked about, they have 4,000 applications, but they can't use them for testing or evaluating. So your collaboration, and be very open to such collaboration. You have my email and things there, Monica. So that would be great. And any questions or so?
So we'll take questions. I'll come.
We use G1 GC with JDK 8 itself. Is it recommended?
Yes.
So then why should we move to JDK 13 then?
So I think you should go to Guild's talk, and that would be helpful. There is definitely, in this track today, we do not have an exhaustive list, but there are lots of improvements that that moving to 11 LTS would bring, and even after that, probably the MTS, as Gil would will talk about. That question. So one of the things that we're doing right now at Microsoft, we have a lot of internal customers who are still at JDK 8. So we're trying to help them to move to 11 update. And we made a list of pros and cons and how it can affect them, like multi-release jars and other things that may be helpful to them. So it's a very case-specific analysis that we have to do. I can just mention all the features all the benefits you can get, but do they apply to your use case? Probably not all of them. So you have to do evaluation of or cost benefit analysis for moving to 11. But remember, any of these kind of low latency garbage collection, or even AOT for that matter, those benefits you will only get when you move to this side of 9. You know? Okay, I'll come to you first, and then you.
You're talking about how a lot of the newer garbage collectors divide the memory into regions. I was just wondering, is that something that's configurable that we should be thinking about, like what size region should we use, or is that something that's just handled by the GC itself?
So it should be handled by the GC. The way ZGC does it is that it is adaptive, I think, on the fly, and so it should not be a problem. Unfortunately, right now it is, and that's what I was showing you with respect to Da Capo. We definitely want to change that, so it shouldn't be something that you should worry about. That was just a bad choice when we started doing G1, so we'll work on changing that, but yeah, you shouldn't worry about those things.
Can you use Shenandoah or ZGC with JDK 8
JDK 8? Not ZGC, but I like that you say ZGC. So, but that's a different thing. So everybody that I talk to always says Z, but I go back to Z. So anyway, that's a different thing. But Shenandoah, yes, I think there is you do get Shenandoah with JDK 8. I'm not sure the status of that right now. If anybody else knows, please. Only the Red Hat one? Okay, so there is, if you go to the, there's a page maintained by Alexei. You could probably go check it out, but you'll have to use their bits for JDK 8. Yes.
Hey, thanks for the excellent metrics. It was very useful. I do have like 2 questions out of this talk. One is, I was also in a talk with GraalVM yesterday when they were talking about the JIT and AOT with GraalVM. And I do see an AOT function with Java that starts with JDK 9. And GraalVM, they also talked about being used in Oracle with Oracle Cloud. Can you help us to decide on like when do you really use the GraalVM AOT versus this AOT? Or do we even start to look into GraalVM or not?
So I'm not the best person to talk about that. If anybody else here would like to chime in, I would appreciate that. I'm looking at you, Mikhail. Sorry. When did you say when you want to evaluate Graal?
Yeah. Is there a difference between the AOT of AOT that natively comes with Java towards what GraalVM is offering?
So the JAOTC tool that I use to generate the dynamic library. It is from the Graal JIT. So you're talking about VM level differences, but this is more of a JIT level thing. Graal JIT is supposedly the future, okay, which means that eventually C2 will be replaced by Graal JIT, not the VM. I think this is a very big question for me to be able to answer, because I'm not the right person to talk about Graal, because I don't want to provide any knowledge that may not be helpful. But yeah, so JIT is different though. I just want to clarify that. So when people talk about Graal VM, sometimes because of the unfortunate, it's similarly named, but VM has a lot of different benefits. So with JDK 9, I think there was a JVM CI, which is the compiler interface that was introduced, and that took advantage of the Graal JIT, and that's how we get AOT. So it's from the same source, I would say, but I have not done any performance analysis on Graal JIT AOT with that. Oh, you know it. Of course, Mark.
I'll talk a little bit about that in my talk later today. I'll be talking a little bit about that point in my talk later today. That talk isn't specifically about Graal. I'm not from the Graal team. I don't represent them. but my talk is about some of the trade-offs in how do you choose whether to use JIT or to use AOT or to use any of the other technologies. So I'll touch on it a little bit. So I encourage you to attend.
So please do, and I was going to talk about that. So Mark, I think I did mention that. I don't know if you were here. So you will talk about the future, the JIT directions. So that would be a good talk for you to attend to kind of understand. AOT is just the start, right? So there's more. So another reason for somebody to move to, the lady asked us, why should I move, right? That's another reason to move, is because of all the improvements that will happen, and it will be on the JDK 8 code base mostly. So JDK 9, sorry.
And the other part would be on the same on why to move. We have seen in like SpecJ 2015, the fork join. It's not easy to use, the different thing we had to do. But parallel stream have been done much better improvement. And one of the things you may want to find, anytime you have the thread pool and within microservice or other situations you want to the auto balancing, it really requires some very well thought. So which is with parallel stream in 9 or higher, you might have better job if you do need the load balancing through thread pool. And it is a tricky issue now because you have if you are within a VM, you might have only 8 core, or your whole system you might have 256 core, and you don't know how your application will behave on those two extremes. So there may be some consideration, but there is no perfect answer to this. You have to try how it is behaving.
Okay, we're at time, so we can take questions later. But thank you all for being here. Thank you, Anil.
Thank you.